Hi everyone, my name is Lydia, and this is what I wish they had taught me about econometrics and introduction. In this video, we are back to talking about the math behind the OLS. In the previous video, we showed all of the math tricks behind the derivation for the beta null hat, and we went through some properties of the derivatives and the summation operator, which are very crucial to understanding how to do the math by yourself for the OLS coefficients. In this video, we're going to concentrate on the math tricks that are behind the derivative with respect to the beta 1 hat. So, as usual, we're going to start from the expression of the minimization of the residual squared. The first order condition in this case is with respect to B1. Keep in mind, B1 in here is our theoretical coefficient. The moment that we step into the derivative, it means we've taken a step into calculating an actual number, and that's why we're jumping right ahead with the beta 1 hat in here. Okay? The first step is exactly the same one as what we saw with the first order condition for the beta null hat. So we've used the power properties on the derivatives. So the 2 has gone in front, and the minus in here is coming because obviously being that it's with respect to B1 in here, we have a minus that is going to go in front of the summation operator. Keep in mind, normally you would have had it in front here, but as we've said, if it's a coefficient that is multiplying a variable, the coefficient can go in front. The next few steps are very self-explanatory, and it's mostly the same logic of what we've seen on the derivative with respect to the B0. So we have simply sent the -2 on the other side, and at this stage, because we have already found a formula for the beta null hat due to the first order condition, where we found that the beta null hat is equal to y bar minus beta 1 hat x bar, we can simply now substitute that exactly in here. Taking it out of the brackets, we're going to have a minus in front of the y bar, but a plus in front of the b1 hat x bar. The next few steps, this is where sort of like the math manipulations come into play. We have simply sort of split this big expression, and we are considering of keeping the yi minus y bar together, but they are being multiplied by the xi, so let's not forget to keep that. And the b1 hat x bar minus beta 1 hat xi, it's all together, again, multiplied by the xi. Because of like a certain shape we are trying to get in the end of the beta null, which of the beta 1 hat, which you have very likely seen at some point in your materials, we are simply doing a little math trick in here. So instead of having beta 1 hat x bar first, we want to have beta 1 hat xi first, which means by flipping them, we switch the signs, and in front now of the summation notation, we're going to have a minus. Then we simply send this entire element on the other side of the equation, so it's everywhere like with pluses. The next bit, we are using the summation notation properties that we have seen before, and because we have simply a constant times a variable, what is happening, the constant can go in front, and we have the constant times the sum of the actual variable. This should explain why the beta 1 hat is going in front. Ultimately, because we are solving with respect to the beta 1 hat, what remains is simply rearranging the expression so that we have the beta 1 hat on one side and everything else on the other side. Now, when you see this expression, you might very easily think, oh, wait a second, this is not the formula that we have seen in previous videos. Or this is not what I have in my books. Most of the times you will see the beta 1 hat, the formula given either as the covariance between x and y divided by the variance of x, or more clearly, you have like in math notation with the summation notation, you've seen it as the sum of xi minus x bar times yi minus y bar divided by the sum of xi minus x bar squared. Now, this is the formula that you are mostly familiar with. So the question is like, well, how exactly do I get from here to here? The thing is, you don't necessarily need to get or like show a very extensive proof of that, as long as you explain a certain property that is, or like a certain identity that it's being used in this case. The identity that I'm going to talk about is extensively used also in other proof exercises. So make sure you keep that in mind, because it's going to come in handy for other types of exercises that you might have ahead of you. The identity is going to be the following. The sum of xi minus x bar times yi minus y bar is exactly the same as if you had the sum of xi minus x bar times yi. But it would have been exactly the same as well if you had instead the sum of xi times yi minus y bar. So all of these expressions, they are equal among each other, okay? There is a very easy way to show it, and we can do it right away here, okay? So let's start from the longer expression. So we've got the sum of xi minus x bar, yi minus y bar. This is equal to, so let's say that I want to prove this first one, okay? It's very obvious that the very first step to get to that expression, I will have to distribute. So this multiplication in here. So it means this entire bracket, I will multiply it with yi and then multiply it with y bar and split the summation notation. By the way, keep in mind for the summation notation, you always have to put like I from 1 to n in here, but just to save a little bit more time, I'm sort of skipping, but keep in mind that the main rule is that we've got the summation notations for I from 1 to n, because you always need like a counter to make sure you're jumping through the loops of the summation notation, okay, of the summation operator. So let's do that. I will have the sum of xi minus x bar times yi, and then minus the sum of xi minus x bar times y bar. Now, due to the identity that I have shown you, it's very clear this item in here is going to stay. However, this one somehow is going to turn into a 0 for us to just have the first element remaining. So let's see what exactly is happening with this particular second element in here. So I'm going to just take it on the side. I have xi minus x bar times y bar. I'm going to distribute again the brackets in there and split the summation notation. So I have the sum of xi times y bar minus the sum of x bar times y bar. Okay? Now keep in mind, y bar is just a constant. Okay? It's just the average. It doesn't have an I in here. So it means like it's not a variable, okay? The y bar is just a constant. And keep in mind, this I in here is indicative that we have a variable, and it's a variable that needs to go through that summation operator. So that being said, I can use the properties of the summation operator and put the y bar in front of the summation operator, and I've got xi, and I'm going to keep the x bar, y bar still the same before I apply another rule to it. Now, for the summation of the xi, we're going to make use of, again, of the average formula. So we're going to rewrite this simply as the n times x bar. Okay? Now, for the last element, according to the same logic where we said that y bar is a constant, well, x bar is also going to be a constant in this case, while if we add the xi, that would be a variable. So if I have x that is a constant, and also y bar in here that is a constant, I have the multiplication, the product of two constants. So it means that the entire x bar times y bar is going to be a constant. So ultimately, I have the summation of a constant, which should give me simply n times x bar times y bar. So as you can see, ultimately, they are the same, cancel each other out, and indeed, this last element that we had doubts that it would turn into zero, we just showed that it actually is zero, okay? The same exact logic, you can use it to prove by yourself that this identity with the second expression here also falls, okay? So now that means that if I apply it, because by that, it means I have simply solved my first part in here. I've solved what my nominator is doing. So now, due to that identity, I know I can write this as xi minus x bar times yi minus y bar. So what about the bottom part? Well, that doesn't change anything. Okay, so even if I have two x's in there, or if I have a combination x and y, it wouldn't change the identity that I just showed you. I would simply write it as xi minus x bar again, xi minus x bar again, but this ultimately is just xi minus x bar all squared. Okay, so by using this identity, you have basically manipulated the math that you got out of the first derivative into what the formula for the beta 1 hat that you see everywhere looks like. I hope this managed to clear up some of the steps that you might have found difficult when doing the OLS proofs by yourselves. Keep in mind these reminders and all of the identities and the proofs that I just shown you could be useful for other exercises as well. So make sure that you brush up on your knowledge on the summation operator, and I'll see you in the next video.